All right, guys, if you haven't already, please get out something with which to write and something on which to write, because we are going to have a conversation. Today, what we're going to do is we're going to talk about the benefits of radians, okay? We have talked about the unit circle, and we've talked about radians, and we've gotten pretty good at converting angles. You might think of the angle of like 120 degrees, and that's 2 pi over 3, or 315 degrees is 7 pi over 4. And so that's what all those angles are in radians. But now it's time to talk about some of the benefits of radians. Okay, and there's two big benefits of using radians. And the first one is finding arc length. Okay, when I say finding arc length, I'm literally saying, hey, find the length of this arc if you had to walk that distance. That's what we're talking about. Okay, and so I'm not sure if you remember, but one of the ways that I defined radians was I said, well, it was where theta was equal to the arc length divided by the radius. Now, for the unit circle, the radius was always 1. So that meant theta was actually equal to the arc length, when the radius is 1. And so literally before, we think about degrees and we think about this gap inside here, but radians is literally the length. Radians are the length of that arc length. And so, or length of that arc rather. And so that's what radians are. Okay. And so we have this idea right here that radians, any angle in radians is the arc length, which is abbreviated as S, divided by the radius. Okay, and when the radius is 1, then arc length is the angle in radians. Okay, so what we can do, though, is we can take that basic formula right here, and we can multiply both sides by r to get S all by itself. And then it would say S, which is the arc length, is equal to theta times r, or r times theta. Either way, it doesn't matter. And so we can find the arc length of any arc by just multiplying theta times the radius. But the catch is this has to be in radians. Okay, that is important. It's got to be in radians. So arc length is this really basic, easy formula right here. Arc length is equal to theta times radius, but the theta has to be in radians. Okay, so what I'm going to do is let's take a look at a couple quick examples. All right, so for this first one, I'm just trying to find the arc length in each one of these situations. And so this first one says the radius is 9, the theta is 2 pi over 3. So therefore, if arc length is equal to radius times theta, then that would be equal to 9 times 2 pi over 3. 9 times 2 is 18 pi over 3, which is equal to 6 pi. Okay, easiest problems in the world. Now, this might get a little bit more challenging with the second one because it says that the radius is 8 and theta is 225. But we know that theta has to be in radians. So the first thing we got to do is we got to convert that. Now, maybe you remember what 225 is. 225 is 7 pi over... No, that's not right. What a lie. That's 315. 225 is 5 pi over 4. Remember, we said all the 45s was always a fourth of pi. So we had 1 pi over 4 and 3 pi over 4. And then the third quadrant, which is 225, would be 5 pi over 4. So therefore, the arc length is equal to radius times theta, which is going to be 8 times 5 pi over 4, which gives us 40 pi over 4, which is 10 pi. Now, they're not always going to work out this nice to be like a whole number and pi, but those two are pretty good. Okay, so this is obviously really simple stuff. So what I'd like you to do is I'd like you to try these three. Remember, arc length is equal to radius times theta, okay? But theta has got to be in radians. So what I'd like you to do is pause the video right here and have everybody try these. All right, hopefully you gave them a shot, and let's see how they went. Like I said, these are just so easy. I don't think there's going to be any problems with these. So this first one, no converting, no nothing. All you had to do is multiply these two. And so therefore, this is going to be 12 times 5 pi over 6. So that means this is going to be 10 pi. Okay, 12 times 5 is 60. So it'd be 60 pi over 6, which is 10 pi. Next one, you look at this one. Now we got to convert this. The radius is 16, but I got to think about 315. Well, I just gave that one away. That was 7 pi over 4. So therefore, 16 times 7 is what? 112. So you got 112 pi over 4, which is the same thing as 28 pi. Like I said, they're not always going to come out clean, but I gave you some nice ones. And this last one, we have the radius is 15 and theta is 30 degrees. Well, radius is 15, theta 30 degrees. That is pi over 6. And so then we get 15 pi over 6, which we can take a 3 out of the top and bottom. And that would give me, 5 pi over 2, or 2.5 pi. See, look, they don't always come out clean. But still, they're a very easy problem. Okay, but now what I want to do is I want to talk about different ways that we can apply these. Okay, and there's two ways that stand out. First of all, we can have an application problem like this. I don't know if you can recognize what I tried to draw there, but that's supposed to be a playground swing. Okay, and in this situation, we could say this is one of those really nice playground swings where we'll say the chains of the playground swing are 20 feet long. Okay, and you're really swinging on this thing. And so I think if you're really swinging, your angle is going to be probably pretty big. And so we'll say the angle through which you're swinging is, I don't know, we want to say like 140 degrees. Nah, that might be a little bit. Yeah, let's go 140 degrees. That's a pretty huge angle, but whatever. Okay, and what I want to find out is, every time you swing from back to front, how far do you actually travel? When you're on that swing and you swing from back to front, how far do you actually travel? Okay, well, this is just an arc length problem. So you go arc length is equal to radius times theta. In this case, the radius is 20 feet and the theta is 140. Now, we don't know, 140 is not on our unit circle, so we have to multiply that by pi over 180. And that gives us, if we make that, we kind of worry about the second part first. We'd have 140 pi over 180. The zeros would cancel out. You'd have 14 pi over 18. So then you could get that down to 7 pi over 9. So we got 20 feet times 7 pi over 9. And that would give me, 140 pi over 9. Now, this is a real-world problem, and so I kind of want a real-world answer. And so I should plug that into my calculator and say 140 pi divided by 9. That's going to be about 48.869. So, I'm going to say about, let's see, everything's kind of pointing towards, 2 sig figs. I went to the nearest degree. This says 1 sig fig, but let's just say 2 sig figs. So I'm going to say it's about 49 feet. So that's pretty impressive. Now 20 feet would be long chains for this, but every time you swing, you're traveling 49 feet. That's pretty awesome. Okay, so now your turn. You try it. What I want you to think about is, let's think about the pendulum of a grandfather clock. Hopefully you know what a grandfather clock is, and if you don't, just picture a pendulum on a clock. And we're going to say that the pendulum itself is some 5 feet long, and that the angle through which it swings is 15 degrees. Okay? And we're going to say that it takes 1 second for it to move from one side to the other, and then a second for it to move back. So I want to find out, how far does it travel in 2 seconds? Okay, pretty simple video, or pretty simple problem. So we're going to pause the video right here, and you guys give it a try. Okay, this is a simple one. The first thing I got to do is I got to go, well, arc length is always equal to radius times theta. The radius in this case is 5 feet. The theta is 15 degrees, which again is not on our unit circle. So we got to multiply that by pi over 180. Now 15 degrees is half of 30 degrees. 30 degrees is pi over 6. So half of pi over 6 would be pi over 12. So maybe you're able to kind of figure some of that out. But I have pi over 12. And so what would that give me? That would give me 5 pi over 12. Now that's one swing, which we said was happening every 1 second. So in 2 seconds, I would want 10 pi over 12, which is the same thing as 5 pi over 6. So 5 pi over 6 is how far it's traveling. So let's plug that into a calculator, 5 pi divided by 6. And we get that, if I go to 2 sig figs, that we get the distance traveled is approximately 2.6 feet in 2 seconds. So it goes about 1.3 feet one way and then swings back about 1.3 feet. Okay? So hopefully this is making sense. Now there's one last thing that we want to talk about with arc length, which is really kind of odd. But see, what I want to do is I want you to imagine we were talking about a very small arc, like I have right here. My theta is obviously very small. Maybe that's a 20 degree angle. Maybe it's a 15 degree angle. I don't know. But what I want us to pay attention to is when I zoom in on that arc, and I don't know how far this will let me zoom in. There we go. Okay, when I really zoom in on that arc, I'm not sure if you notice, but that line actually, or that arc, starts to look like a line. It is not much different because the arc is so small, the theta is so small that the length of the arc and the length of the line, from this point to this point is not much different. So therefore, an arc length and the length of a straight line is almost the same when we're talking about a very small angle. Okay, and this can then have an application. So this was kind of a weird situation to describe, but this can have an application. Okay, if we realize that when we're talking about really small thetas, really small angles, that the arc length can almost be exchanged for a straight line distance. Okay, and let me give you an example of how we could do something like that. I want you to imagine this is you, maxing and relaxing, laying back on the grass, and you look up and you see a plane flying up above. Okay. I'm trying to get this down to your eyes. There we go. Okay, now you being a human protractor said, wow, the angle that plane fills, the mathematical word is subtends, the angle that plane subtends is about 0.45 degrees. Not 45 degrees, but 0.45 degrees. It'd be this little tiny angle. And you realize that is a 747. Which is a Boeing 747. It's a passenger plane. And you recognize that you're an airplane nut and a human protractor. So with those two abilities, you're able to recognize that it is a 747 and that this is 0.45 degrees. Now, you being an airplane nut know that a 747 is actually 250 feet long. It's 250 feet and 2 inches, but, we won't worry about that. So we'll say it's 250 feet long. Now, you realize that as you look up, that airplane is filling this angle of 0.45 degrees, and that the airplane itself is 250 feet long. Well, then what could we figure out if you knew those two pieces of information? Well, what you could do is you think about, what are we missing? We're missing radius, because the plane is kind of taking the spot of the arc length, which is at 250. I've got the theta, but I don't have the radius. And in this case, the radius would be the altitude of the plane. So I'd like you to go ahead, use this information right now, and see if you can find the altitude of the plane. We'll say to the nearest 1,000 feet, because planes fly at like 20,000 feet, 30,000 feet, that kind of thing. So go ahead and find it to the nearest 1,000 feet. So we're going to pause the video for just a second, see if you can find the altitude of that plane. All right, let's see how you did. So I'm going to say, well, theta, in this case, is 0.45. So the first thing I need to do is convert that to radians. So I'm going to say 0.45 times pi over 180. And so I get that theta is equal to 0.45 pi over 180. Now, I don't like to have decimals and fractions, so I'm going to multiply the top and bottom by 100, which is going to give me 45 pi over 18,000. Now, the good news is that 45 goes into 180. So 45 goes into 180, 4 times. So it goes into 18,400 times. So this is the same thing as pi over 400, okay? Now, you can plug this all into a calculator anyway, so it doesn't really matter, but I'm just showing you what that is in radians. Now, we know that the arc length is equal to radius times theta. And think about what we have here. We have the arc length and we have the theta. We don't have the radius. So I can plug everything in and say, well, the arc length is 250 feet. I don't have the radius, and the theta is pi over 400. So I have to divide both sides by pi over 400. And when you divide fractions, you flip and multiply. So r is equal to 250 times 400 divided by pi. And at this point, I can plug this into a calculator and say, okay, so 250 times 400 divided by pi. And I get that it's about 31,830 feet. So as we said, we're going to round to the nearest 1,000 feet. I'd say that plane is flying at about 32,000 feet. Now, that's pretty awesome. Imagine if you had even just some proper equipment that you could measure what angle that the airplane subtends, and you knew that it was about 250 feet long. You could find how high that plane is flying. I think that's a pretty incredible problem. Okay. All right. Now we got to talk about the second benefit. The second benefit of radians. The second benefit is we can find sector area. Okay, so arc length is that distance. Sector area is that surface area. When you talk about a sector is basically part of a disk. Okay, if I chop it up into a piece, think of a piece of pizza or a piece of pie. The surface area of that is called sector area. Okay, now back in geometry, man, we had this crazy ugly formula for arc length and crazy ugly formula for sector area. But again, using radians, the formula becomes so simple. The area of a sector is just 1/2 radius squared times theta. That's it. Now, of course, I'm thinking you would know that theta has to be in radians. It's got to be in radians, okay? Theta's always got to be in radians. So, but otherwise, this is a pretty simple situation. 1/2 r squared times theta, okay? So let's think about an example here. We say, let's find the area if the radius is 12 and our angle theta is 240 degrees. So we know that area is equal to 1/2 r squared times theta, but theta's got to be in radians. So the first thing we're going to do is say, well, if theta is 240, what is that in terms of radian? Well, that's on my unit circle. So 240 is what? That's, 6 pi, no, not 6, 4 pi over 3. Okay, because pi over 3 is 60. And I need 4 times 4 of 60s to get to 240. So that's going to be 4 pi over 3. Okay? And so then I say, well, my area is equal to 1/2 my radius, 12, squared times 4 pi over 3. And then at this point, you just work it out. It's really simple. 12 squared is 144. Half of that is 72. So you get 72 times 4 pi over 3. I'm going to cut in. I'm going to deal with the third first. Third of 72 is 24. So I get 24 times 4 pi. And so there you go. The area 4 times 24 is 96 pi. And so that would be my exact answer. And if I wanted to find a decimal approximation, I'd say, well, and that's about, 302. 302. Okay. And so that's how you'd have it. But however, if I'm doing to the nearest degree, everything would point towards 2 sig figs, which would then mean I'm actually talking about 300, which looks like 1 sig fig, but this part's accurate. Okay. And so these are really simple problems. So what I'd like you to do right now is I want you to try this one, and then I'm going to get you started on some problems, and you can take a break from watching this video. Okay? So go ahead and try this one. Try to find the area if the radius is 15 and the theta is 210. So we can pause the video, give yourself a minute or two, and find the area. All right, let's see how you did. Okay, we know that the area is always equal to 1/2, r squared times theta. That's going to be 1/2 r squared is going to be 15 squared. Theta is 210, but 210 is the same thing as 7 pi over 6. It's on the unit circle, so we should know it. 7 pi over 6. So we go 1/2 of 225 times 7 pi over 6. Let's see. Oh, this might get a little ugly, but who cares? Okay, so we end up with 225 times 7. That's a decent sized number. 1575. So we end up with 1575 pi all over 2 times 6 is 12. Okay, and I think... No, or that reduces a little bit, of course. That would go down to 525 over 4. 525 pi over 4. So that would be the area if this was our information right here. And then if we wanted to go, well, I want to find that to the nearest 2 sig figs. Well, 525 pi divided by 4 would give me about 412.33. So that would be about 410. All right. Now, what I'd like you to do is I want you to try some problems right now. Excuse me. We can... go ahead and stop this video right here. I'm going to pick up in the next video and just work these or show you the answer to these problems. But these problems are really simple. They are on page 146. And what I want you to do is I want you to do numbers 5 through 10. But here's the thing: is it asks for arc length, but I want both. I want arc length and I want sector area for each one, because I just want you to practice these formulas one after the other. And so here's 6 real easy problems. You might have to convert to radians, but it's just 6 easy problems. I want you to find both arc length and sector area. Okay, so go ahead and get started on that. And when everybody is mostly done, then we'll go over the answers and a couple more kind of problems. All right, have a good day.